Now you remember I said on the previous movie, we won't get any numbers because we had no calibrations. This is the bench electronics calibration screens. This is where you will store numbers that describe how many volts gets produced by a certain test pressure on the sensors. And you can see there are no numbers typed in here. When you get a black box from Performance Trends, we're going to send you a calibration sheet. This is the same screen, but it's got spots for us to write in some numbers here. These numbers, if we don't fill them in, can be attained here. There's an offset and a factor for different types of test pressure manometers. We have 1 psi sensors that will go up to about 28 to 30 inches of water, and the 5 psi sensors go up to like 68 inches of water or something. And anyway, so these are the numbers that the program would need, an offset and a factor number. And like I said, they'd be written in here, and you can just, this is a 10 or 6 page, I'm sorry, 6 page piece of paper you would get from us if you bought a black box, instructions for hookup. So that's what we would call a factory calibration. That would be close and get you going. And we're going to do that right now, just to type something in so that you can see how it works. For a 1 psi sensor, or let's say we're on a 600 and 300 bench here. For the incline manometer, we'd use minus 0.109 and 0.00056 for the incline manometer. So let's do that. I believe that's right. I'm going by memory. And let's save that. And if we have a 1 psi sensor, for the vertical manometer, it would be minus 1.67 and 0.0076 are the numbers we would use. You can see here we typed those numbers in, and I just put a comment in factory cal here so I have some idea what it was. You can put in a comment that describes anything you want. And we're going to go see how this stuff looks now. And it says, do you want to keep these changes? I'm going to say yes. This is some example test. And it says, do you want to save them for the current bench as the master bench specs? And master bench specs, I'm going to say yes for that also. Master bench specs have been updated and saved. Okay. Now, what does it mean by master bench specs? We have a test here that was done on a Superflow 600. We could go and pull out of the library this test here that was done on a 110. Yeah, I'm going to say we're going to save our changes. We're going to save them to the same name. And now I will go look at my flow bench here, and it says we got a 110 bench. So we can compare the data on a 110 bench, and it's all being calculated correctly, to, even though our program is set up knowing our bench is a 600. Let's say you got a friend with a 110 or a friend with a 1020, and he sends you files. You can graph them with your data, keep them in your program. Even though your bench is for a 600, we'll keep track of all that for you. And you'll notice when you click on Flow Bench to see the specs, for this test, we ran it with a 110. But here it says these flow bench specs were used for measuring CFM on the current test. These specs are for standard Superflow 110 bench, but your master flow bench specs are set up for a standard Superflow 600 type of bench. The program's keeping track of that, and it's just letting you know if you go into this screen and you get confused at 110 bench. I don't have a 110 bench. Oh, yeah, that's right. That's for this test. The program still knows I got a 600 bench. It's a real nice feature for keeping you out of trouble, but letting you look at tests from all sorts of different flow benches and overlaying graphs or making reports or whatever. But we keep track that your master bench is a Superflow 600, and like we had just told it, we now have a black box 2 with certain calibrations. So let's go back and pull back that old test that we were playing with. And I'm going to show you a little tip here. This is on the Pro version. In the history log, I clicked on Open from History Log, and this is a chronological list of everything we've been working with. And you can see here, this is that example test. I'm going to open up this test, which is this. Here's the test we're working on right now. The example SB4, small block 4. But the small block Chevy, example small block Chevy, is the one I'm going to open up. It was the second to the last test. Here's the third to the last test we worked on. Here's if you go down here, I've got this thing open. Yes, I want to open that test. But it keeps a chronological list of everything we worked on. And if we go back in here and just double check, here we got those calibration specs. And I just want to show you that now, oh, it's got some other feature turned on. But now when it gets communicating, you see we got some actual numbers flickering. This is another clue that the box is communicating with your computer. If it wasn't communicating, you wouldn't see this little bit of flickering. And if we go make a change here, see how it's going up and down? Well, I make little changes here. Now you're saying with the bench not running, why is it reading anything? Well, that's because like when most systems, you have to re-zero them. They do drift off a little bit, and that was a factory calibration. So we have this command under options to re-zero the pressure readings, and it says, yep, I want to re-zero them. It said there was a significant change, and it says, do you want to keep them? And I say yes. And it's telling me that this will not back calculate anything we've done previous to this. It only affects data coming up. So I'm going to say, yep, I know that. And now you can see we're, again, flickering a little bit, which is a good sign. You want to see it changing a little bit. It's only a 100th of an inch. And now you can see we're getting flow readings here also. So those two are reading now. You can see here after we read zero, the readings are reading 0. And there's a lot of other options here, including troubleshooting again. You could eliminate the re-zero correction, see what the raw calibration was. Re-zero tumble and swirl meters. It activates some foot switches or hand switches and stuff. So there's a lot of things that are available under options, and then under help, again, you can see a lot of troubleshooting things here that we have developed over the years. But before we get into actually starting and running a test with electronics, let's go over some of these screens here that are kind of important, so at least you know what we need to get going. Head specs. This describes the head and is good, useful information for, just keeping records of what heads you flowed, a nice record of things given to the customer and stuff. And some of these things are used by the program. For example, is it a 2-valve or 4-valve type of head? Do they Siamese together into one port, or they say it's 2 separate ports, things like that. Valve diameter and stem diameter and throat diameter and seat angle. We have some preferences, so you can turn on some detailed analysis to try and exactly figure out what the flow area is based on that. But you remember that little curtain area thing that we had. This information is used for that, for those calculations. Port shape, rectangular or round. This is primarily used for when we start doing port velocity maps. Are we going to do a round port or a rectangular port? Port volume and stuff is again used to somewhat draw a rectangular port for port velocity, and it's used for some other more advanced calculations that the Pro version has. Same thing on the exhaust. A customer, you can develop your own list of customers and stuff. Head number, some shops are real fussy on making sure everything's got a head number. This one doesn't have a head number. But down here is something that's really pretty important. Cylinder numbering. Number of cylinders to test, and here he gives you a little preview. So 1357 is like a typical Chevy head. Let's say you had a Ford head. The step size wouldn't be 2, it'd be 1. So the cylinder number would be 1, 2, 3, 4 on one side, and instead of starting at 1, we'd start at 5. It'd be 5, 6, 7, 8 on the other side. So you can get pretty much any kind of cylinder numbering you want, and how you enter these numbers here, how many cylinders on the head, what the step size is between cylinder numbers and the starting cylinder number, is going to affect all these tabs up here, so that things are going to make sense to you when you give them to your customer, or so you can keep track of which port where you're actually running. Now, some people don't want to do that and keep track of different ports on a head. What they want to do is they want one port, and they want to just do different modifications or claying up a port to try and get it to flow better. And what you can do then, we're still going to call it cylinder numbering, but you might just want to start at 1 and go with as many as you can go, with up to 8. And instead of these being cylinder numbers, they're still going to be called cylinder numbers, but it might be baseline, and 2 is modification 1, and 3 is modification 2. And you can keep track of all this stuff here in comments. You can see I backed out of that screen by just clicking on something else, and you can say here, uh, I want to say as, not as. Okay. And this is how you keep track of things on comments. Comments are very useful because there's different things that we're not going to ask for that you might think is important, like, I don't know, valve stem seals or something. Well, actually, we have a place for that. But there might be some information that you want to keep track of. The place you do that is in test comments here. You can keep track of anything you want. We just did head. Let's look at this other thing up here called head details. Here we keep track of just about anything else you might want to think of. And you think, well, why don't we just keep track of it in test comments? Well, because this keeps it nicely organized for things, for printouts and stuff, that it's always there, it's always recorded the same, and you can carry over a lot of this information from one test to another. Um, anyway, minimum cross-sectional area will do a little calculation for you here. If you say it's 1.8 in height, oh, what did I do there? Yep, I see you. Okay, the width is 0.7, and the height, yeah, it doesn't like that until I put something in here. There we go, 1.8. And you can see it calculates out in an area of 1.26. Or if you change the area to 1.4, it will adjust the other two to make sure that it equals the area of 1.4 square inches. Material, what kind of locks you're using, all sorts of information. You can see where we got descriptions here. When you click on it, it actually expands it out, so you can put a fairly long description in there. And anyway, so that's head details. Flow bench and see details of calibrations. We kind of covered that. The other big one is test options. This one is really has a lot of information that's going to describe how you're going to do this test. What test pressure you're trying to run to. We said 28 is common. Superflow actually does a lot of things at 25. They recommend 25 for a lot of things. Number of rows of data, we got it set at 18. And that is, you can see 18 over here. That's how many rows of data you want to fill. Now, there's no downside of having more than you need. Some people just like to only allow 6 or 8 spots there, but there's no really downside to have that higher. But let's say we change that to 10 just to show you how it works. The bore adapter diameter. This is very useful. This is how you're simulating your cylinder head when you do your testing. If you flow tests or flow a head on a 4-inch bore, and somebody else flows it on a 4 and an 1/8-inch bore, you're going to get different results because the valve is going to be shrouded a little bit different by the bore, and it could be a potential reason why your results are different than somebody else's. So it's very good to always put this in there. Another thing that really will affect results is what kind of intake and exhaust adapter do you have? For example, do you clay it up? Do you have a special radius inlet you use? Are you putting the actual manifold on it? Or if you can see here in this drop down, it gets highlighted. You can actually type in most anything you want. Maybe you got a special adapter that you use on this. Maybe adapter 22 you guys call it on your shop. And that's what you want. In this particular drop down, we have a drop down. You can also type in something else that you might want because we figured we couldn't think of everything. On the exhaust, same thing. A little short stub stack. There might be no adapter, exhaust manifold or header. And this will definitely affect the results. So this is very good for you keeping track of how you're doing your test. What are you going to record? Obviously, CFM is what you're going to want to record, and give you a couple choices. Calculate from data entries. That is what you're going to use almost all the time. Data entries means from flow range, incline manometer, test pressure. We're going to calculate the CFM from that. Sometimes you saw a flow bench test in a magazine and you just want to graph it out. Well, you can enter CFM directly. We don't care how you got it. So if you do that, you're going to just get, well, I'll just do it here. Enter CFM directly, no calcs. I mean, we change just to 10 rows only. Let's see what happens when you change that. We got lift, L over D, and CFM. You're going to type that in. With that lift, I got this much CFM. And you can see we shrunk this up to 10 rows here. But that's not usually how we do it. We usually calculate from data entries. There's another choice here. Calculate from entries and include stability. Now that's only useful if you got a data logger because we have a way of mathematically calculating what we call stability. A lot of test porters are interested in, does the head pulse when they're trying to measure it? At low lift, it may not pulse. At higher lifts, it might whoa, 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 start pulsing, and they want to know that. And we can actually uh, come up with a mathematical measurement of that. How much is the test pressure jumping around with our vertical test pressure sensor? And we'll actually fill that column in for you with a measurement of how much was the test pressure jumping around. Temperature. If you have a 110 bench that needs the temperature corrections, this will automatically be enabled. Um, and sometimes you might just want to record temperature even though you don't use it in the calculations, like on a 600. There is a temperature sensor, I think, in a 600, and you can do it. You might want to record or don't record barometer. Sometimes, like a Flowcom does have a barometer sensor, and you can record it. Um, or you might want to just type it in yourself. We don't use barometer in any of the calculations, but some head porters just want to use it. You can record humidity, either percent or dew point. Swirl, we have swirl meters, and you can measure swirl. Tumble, you can do this. I'm just going to show you what's going to happen. And tumble settings, you can come up with whatever you want. There's tumble settings to be from 0 to 270 degrees of rotation, let's say. And let's see what we've done here. Yep, I want to do that anyway. And you can see we've added a whole bunch more columns here of swirl and CFM stability and barometer and a lot more stuff here. Now we got a scroll bar down on the side because it all will not fit on the screen. We got our tumble measurements here, swirl, place for swirl. You can type in a number and record it. Go back to test options. I'm going to get rid of some of this stuff because it really starts getting cluttered if you do things that most people aren't going to do. I'm going to turn off a lot of this stuff. We're not going to record all this stuff. Okay. Valve lift settings. If you start with a blank test, it's going to go to this information here to generate a bunch of lifts for you automatically. And what type of valve lift settings? This test is using L over D as the increment. And you can see here that the L over D is incrementing in nice even 0.05 increments because it's not an exact, the lift is incrementing at something different at 0.101 because these people wanted to do it even lift over diameter increments. And there is a reason for doing that, but I mean, most people don't do it that way. So I'm going to change that. We're going to increment it even in from lift inches or inch increments. Do you want to include a 0 point? You do typically you want to do that if you're going to record leakage. Leakage is what does the head flow when the valve is closed. And any flow you get when the valve is closed must be coming from leaks, sources of leaks. Um, and it's just a way of correcting the data. Ideally, you want leakage to be very close to zero. If it's not, you should probably try and find the source of the leaks and fix it. But measuring it and correcting for it is something you can also do. Let's say we want zero point 0.6. Here it gives a preview of what we're doing. I'm going to have to bump this up now to 20 because it wouldn't fit. You wouldn't get, for what I had set up there, you wouldn't get that many points in just 10 rows here. Okay, do you want port velocity measurements with a pitot tube? You got several different options here. You can record 9 different points across a cross section of the valve at one lift or at 2 different lifts. You can record one velocity at all valve lifts. And this is typically not a velocity. This is typically maybe the carb guys who flow carburetors want a measurement of venturi vacuum at different throttle angles or something. They were the people who would use this. So this gives us one place to put data from that third pressure sensor that's either on a flow com or a black box. So you can get one data point while you're measuring CFM. Here's something the wet flow guys would want to use is record a picture file at all the valve lifts. You got a separate picture file that you want to record with it to display in the data. And like I said, wet valve flow, when they take a picture of the wet valve flow, this is where they would choose this selection anyway. But let's say we're going to record 9 port velocity measurements uh, at 2 different lifts. And how do you want to do? Enter the velocity directly. Do you want to correct for the barometric pressure if you're using a flow com? Or do you want to enter the test pressure in inches of water? For example, if you enter it in test pressure in inches of water, you would see something like 10 or 12 inches of water pressure. But what a lot of people would rather do is convert that, let's say 10 inches of water pressure into a velocity of maybe 120 feet per second, or if it's 140, whatever, do all the math on it. And if you got a barometer reading, you can actually correct for the barometer if you want. The barometric pressure will change the feet per second conversion from inches of water to feet per second. And this gives you that choice. You can do it with our black box too, but you've got to ask to get a barometer sensor installed. And there really is not much advantage to it because you're not so much looking for the absolute flow velocity as much as you're looking for what is the difference in flow velocity across the cross section of the port. Like, is it high velocity in the upper left corner and it goes to very low velocity in the lower right corner? And if you correct for a barometer or not, you're still going to see the same trends. So there isn't that much advantage in doing that. Okay, so we're going to back out of this screen. And you can see here it says we have not set our list to record this velocity at. Yep, I want to return here and I want to put in the list we want to record this velocity at. And I'm going to say we're in inches now. I'm going to say we want to do it at 0.3 inches and 0.6 inches of lift. And now you can see it lets us back out. And now we got 20 rows of data. But you can see it did not change this over here. That is because we already had data assigned here. If we were starting with a new test and we made this change to get these increments in, it would have made the change. But it's not going to screw up an existing test because you've already got data in there. So what I'm going to do, and I'm covering a lot of things for you. We haven't even gotten to the point of starting a test from scratch. But I'm just trying to show you a lot of different options here. If you click on the top row of the description here, it gives you different options here. Like you can erase the column, you can copy the column down, you can copy the column down at this value. So what this means, copy column down, is whatever it sees here, it's going to fill in everything else with the same number. So it would fill in range 2 for everything. And that's useful let's say you know you're going to have 25 inches of water here, and you want to fill everything in with 25 inches of water rather than typing it one in. I'll show you here in a second. Let's just do this. I'm really making a mess of this test, but we got a copy of it already in the library, so it doesn't matter. But let's say we did this, copy down column. I'm just going to copy down the column at the valve list, and you can see it filled everything in. I'm going to copy the column down, and it fills in everything, even if there was a valve lift there or not. I'm going to click over here. I'm going to generate lifts based on what's entered in those test options screen there. And you can see there we generated the lifts, and the LVDs came with it. Let's say we're going to do this. We know we're going to do range 3 for everything. We're going to do this. We're going to erase the column, copy the column down at valve list. So there's a lot of fancy things you can do there. You can click over here in this column. You can insert a blank row, delete a row, erase a row. I'm going to insert a blank row. It says it's going to drop row 20 off the bottom. So do you want to continue? I'm going to say yes. And now we got a blank row. Maybe we want to put in point 125 and have a data point at point 125 or something. You can see our graph is all screwed up because this CFM data doesn't correspond to anything we did in the real test. So that gives you a little overview of some of the powerful features in the program and with some of these basic screens, how they're used.